morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 4, that is the distribution network OPF analysis. So, today we will start on developing the multi-period OPF and how to develop that problem and how you can solve that problem. So, till now whatever OPF methodology we developed, that is the minimization of, let us say we are minimizing the loss. Okay, how you write that equation? We write it that summation of n equals to for all the buses, then m for all the buses, then L n m and R n m. That is for a single time step. We did it for a single time step and it is not time coupled or for the entire time horizon. But and also the DERs we considered, that is of PV inverter type. Okay. That means their operation, the output of the PV inverter is not time coupled operation. But if we consider battery DER, we have seen in the module that if you design a battery and then if you do the energy update, their energy update is a time coupled constraint. That means energy level for the next time step depends upon the energy level of the current time step and also how much charging discharging is happening in the current time step, that we are considering. So, that means it is a time coupled constraint. This is called time coupled, where the present future time decision is coupled with the decision of the present time step. Now, again if we see the voltage regulators or the capacitor banks, we have introduced these two reliability constraints, if you can remember, that will prohibit the total number of the switching or the tapping operation for the voltage regulator and the capacitor bank. That means multiple tap changing or multiple switching is not promoted. If that is that, then you can see that equation also has this total time period terms. That means the total tap changing should be of summation of t. So, this is also a total horizon time coupled constraint. So, if you take battery or voltage regulator or capacitor bank, you will get constraints which are not time independent. You will get the constraints which are time dependent. So, if you take single time step decision for this kind of a problem and solve them, these are mostly named as greedy solution at each time step, then that solution may not be optimal or that may not obey this time coupled expression. That means, let us say you are saying that total tap changing will be summation of that time from t equals to 1 to capital T, tap of t minus tap of t minus 1. We are saying that it should be less than of some value. If you do the tap changing at every time step independently and you say, let us say this nt equals to 60 and your time step is, let us say 15-minute time interval. So, that means you have total for the 24 hours, total 96 time intervals, and but the allowable tap changing operation is only 60. So, let us say if you take a greedy solution, then from the very first time it will start doing the tap changing operation. So, if your load profile is like this and you start from here, then when your peak will come and your voltage will fall at the minimum level, you have no option of doing the voltage regulation operation. So, that is not good thing. The same thing we can see for capacitor bank, the same thing we can see even for the battery, that let us say we start from this time step, from the initial time step, and the battery is charging discharging is happening. If you do not consider the long term benefit, that means when the battery should discharge at the peak time, the battery will start discharging at the off peak time, and whenever you will reach at the peak, you do not have stored energy in the battery. So, that will reduce the efficiency of your algorithm. So, here you need the multi-period OPF, where you need to develop the algorithm as a summation of t. So, a multi-period optimal power flow problem is an extension of the standard single time period OPF that optimizes system operation over multiple time steps, typically to account for time varying loads, generation and storage dynamics. Okay? So, MPOPF is generally formed as a cost or loss minimization problem, and it has the constraint which has the time coupled constraint like storage energy level. You have varying demand and renewable generation profile, and you have network and device constraint like the each time step we considered in the last lecture's OPF problem as well. So, the objective function for the multi-period OPF or MPOPF is the summation of the total cost. So, that is the variation between your single time step OPF and multi-time step OPF. If it is a single, then you are just minimizing of the CT, but if it is a multi, then you have to minimize the summation of CT. That means, we want to get the solution for the each time step will take care of the future as well. That means, your present decision is a good decision for the future as well. So, that will be your multi-period OPF main motto. So, the decision variables are active and reactive power at the main substation, active and reactive power dispatch from the DERs, voltage magnitude and angle, storage charging discharging, tap position of the VRs and switching status of the capacitors. These three things we have considered for the single time step as well. This is the extra thing will be added for the decision variables when you go for MPOPF. And depending upon that your system condition, you can either have battery, you can either have voltage regulator only, or you can either have only capacitors, all merger of all of them in your system. Got it? So, the constraints are active and reactive power balance equation at each time step, voltage and power flow bounds, then your operation limit of each DERs, and with that extra constraint you have, that is intertemporal constraint like stored energy balance and your voltage regulator and capacitor bank reliability constraints. Okay? So, a typical MPOPF problem in mixed integer nonlinear or non-convex programming framework, you can see it like this. The MPOPF framework is proposed for distribution system considering DERs and the batteries. We are considering only the PV and the batteries. Okay? The OPF problem is what? It is minimizing the total energy purchase cost. This is your cost per unit. This is your power purchase from the substation through the substation, and this is your time step. So, this is the total cost for running the system for the entire time period. So, similar to the single time period, you have your power balance constraint. Addition to that, you have this battery constraint as battery charging and discharging variable as well. So, till that point you had for your single time step. You have extra this two charging and discharging variable, which will be adding charging as a load and discharging as a generation with the power flow, that will be added because of the battery. Same thing you will see for the reactive power as well. We are considering this only one variable for the reactive power, and that will be ranging from minus to plus. If it is minus, that means it is supplying, and if it is plus, that means it is consuming. Okay? Then you have your voltage constraint and you have your nonlinear equality constraint. Your voltage limit, your charging battery charging limit, your battery discharging limit, energy limit and your binary constraint, that we have already discussed in our modeling portions. And apart from that, you have this time coupled constraint, right, and your inverter, battery inverter, reactive power support constraint. With this, if the previous problem is a mixed integer non-convex problem, right, you have your integer variables, these are your integer variables and this is your non-convexity. So, this is a mixed integer non-convex problem due to the quadratic equality constraint and the binary status of the battery variable. Now, solution to such problem is complex and high chance of providing local optimality. to remove the binary variable. That binary variable normally we used for avoiding the simultaneous charging and discharging. So, if we can get rid of this binary variable, that is at least in our hand, if we can do it, then your problem will become only a nonlinear programming. It is a non-convex, but still it a nonlinear programming only, without having any mixed integer constraint. So, that is comparatively easier to solve compared to the mixed integer problem. So, to avoid this simultaneous charging discharging, we are replacing that binary variable with a penalty cost function added with the objective function. That means, this cost function extra is added with the objective function to avoid the simultaneous charging and discharging. What this objective function says? This says the loss function because of your charging and your discharging. Now, why this will avoid your simultaneous charging discharging? This is because either your loss function will give you the charging loss or it will give you the discharging loss. Now, you can see it is minus here and it is plus here. Okay. So, that means there is a penalty whenever you will charge, and there will be a less penalty or addition of the reduction of the penalty cost whenever there is a discharging. Okay. So, simultaneously one function cannot increase or reduce together. So, this value can either be increasing or be decreasing. If that so, then we can say that either the charging operation will take place or the discharging operation will take place. So, that is how you can remove that mu term from your power equation, and the same other equation will remain same. So, we will solve this problem and we will see what are the results. So, this is solved for an IEEE 123 bus test system considering only 10 time steps. Okay. With the 85 nodes have your loads, and we converted this unbalanced IEEE 123 bus test system to its balanced version by considering only the positive sequence network. Okay. So, positive sequence network is a balanced version. So, we are taking it, and additionally we are adding 17 PV inverters and 26 battery inverters in this network, okay, and solving the centralized OPF problem. This is your input data corresponding to your solar irradiance, loading and your cost. This loading factor shows that the multiplication or the multiplication factor with the base load. So, we have varied our load from 0.2 per unit to 1 per unit. Okay. So, this is the solution we are getting. We have shown the results for 3 different batteries located at different locations of the network. You can see it is a bus number 87, it is bus number 3 and it is bus number 116. So, that means one battery is at the very starting of the network, one is at the middle of the network, and another is at the end of the network. So, if you notice that the battery charging and the discharging at the overall network is at the same place almost, though their volume of the charging discharging is not same, but almost their charging discharging is synchronized, okay, and no simultaneous charging discharging is obtained or is observed. Okay. And due to that, if you see the substation power, what you wanted, that if you see here your cost is low, then you have higher cost. From 4 to 7 you have higher cost, then 7 to 8 you have lower cost, and then again 8 to 10 you have higher cost. So, if you see that the charging operation happens between 7 and 8 when your energy cost is low, and discharging operation happen between 5, 6 and 9, 10 when your energy cost is very high. That means, your battery is operating to support that network to achieve the lesser cost, and depending upon that you can see that your power purchase from the substation is also reducing from 4 to 5 and 6 and increasing at the 7 and 8. Okay. Now, if you see the decision variables, number of decision variables for this problem, it is around 6300. Total linear constraint is 11,636 and nonlinear constraint is 1270. Okay? And we validated the same problem with the control actions in the OpenDSS platform. So, OpenDSS platform will give you the actual nonlinear power flow solution for your control decisions. If you validate it and get the real powers at the substation, if you see that they are almost equal, your line losses are also equal. Then, but if you notice the solution time for this only 10 time step solution, we took only 10 time steps. For 10 time steps, and that is also an hour time step. If you take it, then it is coming out to be approximately 80 minutes, right. You have your solving the entire horizon. Now, you can imagine that 10 time steps is taking 80. So, if you take 15-minute time step, that means you have total 96 time steps, how much time it will take to solve the overall COPF problem if you solve the entire summation of T together. Okay? So, solving the entire multi-period OPF problem as a single large optimization becomes computationally very expensive and interactable for long horizon or long networks. You cannot track the solution process. The solution time for previous case is almost 80 minutes for only 10 that I just told. So, if you can decouple the time option, that means you can solve each time step differently. You will first solve for time step 1, then you will move for time step 2, then you will move for time step 3, then you are in a good solution algorithm, if you can do it. Okay? So, time decoupling if you can do, that will break the problem into smaller sub problem, one per time step or block, significantly reduce the computation time and memory use. You also need not to take entire data together for that 24 hours or 96 time steps and solve them together. For that also you need a huge computation facility, that also you do not need. So, if you can decouple the problem and solve each and every time step separately, then that will be a efficient solution process. So, that is called the real time and rolling horizon application of the multi-period OPF. So, if all the power system operations mostly are done in 5 or 15 minutes. So, if you get a solution algorithm which can give you solution within 5 minutes time, that means your algorithm is fit for the real life application. So, time decoupled approaches are better suited to rolling horizon strategies where only a few time steps are solved and implemented at a time using forecasts that are updated frequently. So, you can take the updated value, you solve for the next time step, you give the decision, then again take that new updated value and then again solve the decision. But you have to keep in mind that whatever real time solution you are doing or you are solving for each time step, that has to take care of your long term benefit. That means your total time coupled benefit. If it is not, then it is just a greedy algorithm. Okay? So, challenges with this time coupled solution. First, time coupled MPOPF can accommodate the long term benefit that I have told. That is the advantageous attribute of your time coupled OPF formulation. If you decouple them, then decoupling the time steps can weaken the coordination across time. That means, if you are breaking the time coupling, if you break it, then that advantage you cannot leverage, right. So, potentially leading to suboptimal or infeasible solution point. That is possible, that you are getting a solution that is not globally optimal or long term benefit is not restored. So, that means that is not a feasible solution if you do the time decoupling. There is a high probability of getting that kind of solution. So, asset like batteries, load shifting, voltage regulators and capacitor banks needs to be coordinated control over time. So, proper modeling of such dynamics is difficult without full temporal integration. Okay. So, greedy algorithms works as a time decoupled method, but that is a short sighted topologies, because it will take the decision for that time period without considering its effect on the future time steps. It is a greedy algorithm. We call this kind of algorithm greedy algorithm. Okay. Topologies as the optimal decision obtained only by considering the present events and neglecting the influence on the long term benefit. So, if we can generate or derive a real time OPF problem which will take the consideration of the long term benefits, then that is the exact method we are looking for. So, we will derive that. So, let us take an example of an OPF problem which combines the direct load control, that means you are controlling or doing load shedding at the real time at few buses of total energy requirement at each phase of a particular node, and severe techniques are implemented in the real time OPF. So, severe, I told that it is good when you want reduced power for voltage dependent loads. So, this is the architecture. Your network has an ROPF engine, that is a real time OPF engine, data acquisition system for solving and gathering the information. You have meters, you have load controllers, you have capacitor bank controllers, voltage regulator controllers, and batteries, PVs, and other DERs. Okay. So, we will try to move forward with this example. So, the problem says that you have to minimize a certain objective, we will come to that objective with the AC power flow equation. We are following the AC 3-phase power flow equation. The assumptions are, it is perfectly 120 degree apart, and angle difference between phase currents are considered to be constant. So, actually we are using the simplified BFM model of 3-phase distribution network. Okay. We are using that. So, the input data does not change within 2 successive intervals. That means, if we see the time and it is varying like this, it may be a 5-minute time step, but within that 5-minute time duration, your input data, that means your load or solar generation, is not varying. That is our assumption. If you can reduce that 5 minutes, then it is fine, but at least for that time step we are assuming that it is not varying. So, the approach is, we are going for centralized real time phase load control, reduce the phase voltage to reduce the demand, and operate voltage regulators, capacitor banks, and smart inverters to keep the phase voltages within safe limit. Okay. Our decision variables is capacitor bank switch on off status, your voltage regulator tap positions, load demand at each phase, because we are using direct load control. So, we have to determine how much we have shaded out or how much we have restored. So, you have to determine the load demand at each phase and active and reactive power dispatch from the smart inverters. Our input data is energy price, unregulated per phase load demand, and the solar power generation. So, you have used the load model of the ZIP load model. This is your active and reactive power load model. We have seen, we have using direct load control, that means load shedding. So, actual load must be within the critical load, that is the minimum load possible, and the unregulated maximum load. So, that is the constraint for direct load control or the load shedding. You cannot cut out the entire load for the time period. It has to be, the critical load has to be restored all the time or met all the time. So, this is your load model. Now, you have DER models. This is for PV inverter and this is the models for your battery. Okay. So, this is for your voltage regulator models, this is your capacitor bank model. So, we have studied all these models in module 2, and this is your unbalanced distribution network model of simplified 3-phase BFM model. And last, we have considered this is your phase voltage unbalancing rate constraint, that with all these expressions or all these actions of load shedding, voltage regulators, capacitor banks, DERs, your unbalancing effect can shoot. So, to reduce that and to keep that within a certain limit, we are using this PVUR constraint. So, the objective function for this problem is first to minimize the total energy cost, okay, and plus the dissatisfaction cost. Why this dissatisfaction cost? Because we have used the load shedding operation. So, if you perform load shedding operation, then that will cut some of the loads from the consumer premise, and if someone is forcing you to live in dark, then the dissatisfaction level of yours will increase. So, that is why this is added as a monetary penalty with the objective function. So, you can see these two are self contradictory or complementary with each other. If your energy cost is lower, then you will do more and more load shedding, but that will enhance your dissatisfaction cost. So, that is actually a multi objective problem. So, if you form this problem as a day ahead or offline or time coupled problem, then you can write it like summation of T Ft subject to all the network resource constraint and the reliability constraints. What are these reliability constraints? That total average time average load shedding should not be more than a certain limit. That is your quality of service. That is your quality of service. So, that quality of service has to maintain all the time. Then your voltage regulator safety constraint and your capacitor bank safety constraint. Okay? But if you go with the traditional time decoupled greedy algorithm, that will minimize the cost for that time step, and it will always try to maintain the load shedding percentage of load shedding below that quality of service limit all the time. It is not like it total time step it is trying to minimize, it will keep every time step it will try to restrict the load shedding operation, and this two constraint it will not consider. Okay? But if we take this new real time OPF formulation, then you can see that objective function is reformulated as limit of t tends to infinity 1 by 2 expected value of t. That means, for a long time you do not know what is the value of t, how much you have to run. So, if your total time step is going to infinity, for that time step as well your total expected cost, because now your cost has become stochastic. So, for that expected cost your time average cost at the each time step will be minimized. So, this is your long term benefit is added. Similarly, for long term load shedding average is also added, and your capacitor bank and voltage regulator constraint is also added in the same method, that if your T is infinite, at that time also it will restrict the operation of the load shedding and as well as tap operation at each and every time step. Okay? So, now this is a huge problem with a non-convex constraint. So, we have to solve it. So, for doing that, first we adopt the linearization method. So, auxiliary variables we can use for the max function, absolute function and the bilinear terms to convert them in a linear counterparts. So, McCormick envelopes normally used for multiplication of two continuous variables, that is also a bilinear non-convexity, and first order Taylor series expansion for linearizing the quadratic constraint. So, if you see how we can do it, if you have a max function of two variable or negative of this two variable, you can just give a replace with the auxiliary variable z, which will be greater than equals to your variable inside the argument. Okay. For auxiliary variable as well, if mod of a minus b is less than equals to c, if that is your constraint, then you can define an auxiliary variable d which will be less than equals to c, but greater than equals to a minus b and also b minus a. So, all the condition the d value will satisfy your mod value. So, we will replace that one in this expressions and make them linear. Then you have bilinear terms, which is a multiplication of one binary and one continuous. That also you can see for the capacitor bank switching. Your capacitor bank, this is a binary, right. So, if you do that, you can replace them with a auxiliary variable x equals to mu p, where your mu is the binary and p is the continuous and x is the auxiliary variable. So, to do that, you can think these two extra constraints you have to add with your system. If you add it, if your mu is 1, then x will be within p min to p max, and your if in this constraint if you put mu equals to 1, then your x equals to right? But if your mu is 0, so at that time your x will become 0, less than equals to 0, greater than equals to 0. That means x equals to 0. And here if you put, then again it will become p minus p max, p minus p min. That does not mean anything, because already you fixed your x to be equals to 0 value. So, that will reflect how you can represent the bilinear terms as a linear equivalent. McCormick envelopes are used for two continuous variables, that you can see for the ZIP load model. When you multiply this load, because this is also your variable, you this load with this voltage equations, because this is actually your W is actually V square by V nominal square. So, you do not know this V, right. Similarly, your U is V by V nominal. Okay. So, that means you have a multiplication of two variables, continuous variables. So, you can represent them as this McCormick envelopes, which possess 4 inequality constraints with the optimization problem. Then first order Taylor series expansion for this quadratic terms, equalities and inequalities. So, if you do that, and first order Taylor series expansion, if you do for a certain initial point, you will get this equations. What it says, that first you take the initial, then x minus a del f by del x at that initial point, then y minus b del f by del y for that initial point. Like this, we will expand these equations, each and every quadratic term, and we will get the revised solution. So, we got whatever till that point, all the constraints we have modified and relaxed the non-convexity and made it a linear. Now, we will see that your objective function is what? 1 by t limit t tends to infinity summation of your expected value of f t, right. How to deal with this kind of expression? You cannot deal, right, and still your time coupled expressions, your battery and your voltage regulator, those are still there. To remove that, generally virtual queue method is used. What is this virtual queue? This virtual queue says it starts with a value 0, and each and every operation that will enhance the length of it. That means, if you see the 4 queues has been defined, one is for load shedding, one is for tappings, one is for switching of the capacitor bank, and one is for battery operation. So, every battery operation or each voltage tap changing operation, the length of this queue will increase, and with every increment, that means that will denote that you are doing that battery or the voltage regulator operation. That is an notation, or you can say alarm to the network operator. It starts with the 0 value. So, the virtual queue, it aims to preserve quality of service and to avoid unregulated battery operation with less tap changing operation of the voltage regulators and switching operation of the capacitor banks. The optimization problem will try to prevent the length increment, because you do not want your battery operation to be done multiple times or frequently, or your voltage tap changing operation multiple times frequently. So, you have to restrict that. So, the length increment of that queues must be restricted. So, that is done by imposing this constraint, where we say that for time t equals to limit t equals to infinity, the expected increment of your queue length is 0. That means, queue is not increasing. If that is satisfied, then you will say, then my operation is settled. So, but still you have limit t tends to infinity expressions that you cannot implement in a classical optimization problem. So, to relax that as well, Lyapunov function comes into rescue. You can use Lyapunov function. What is Lyapunov function? A Lyapunov function is a non-negative scalar measure of the multidimensional state. That means, when you have multiple queues, that means your problem has a multidimensional restrictions on that OPF problem. So, if you use Lyapunov function, that will give a scalar measure of that multi-dimension. Lyapunov function are used extensively to ensure different forms of system stability. The state of a system at a particular time is often described by a multidimensional vector. A Lyapunov function is a non-negative scalar measure of this multidimensional state. Okay? Typically, the function is defined to grow large when the system moves towards undesirable state. That means, when your Q length is increasing, at that time your Lyapunov function value will also increase. Okay? When your Q length is increasing, your Lyapunov function value will also increase. And by looking at that Lyapunov function value increment, that is an alarm to the distribution network operator or the energy scheduler that your system is going to an undesirable state, and you have to restrict that increment. So, system stability is achieved by taking control actions that make the Lyapunov function drift in the negative direction towards 0. Okay? So, you can define the Lyapunov function. For achieving the stable condition of the drift of the Lyapunov function should be minimized and made close to 0. So, if it is 0, that means you can say that your battery operation is only needed, or voltage tap changing operation is only needed when it is absolutely necessary. You will not do unnecessary operation at the real time, and that will give the restriction or keep the time coupled operation in action. So, the Lyapunov function is defined like this: half of weighted summation of the square of all the Q's. Okay. For 4 Q's, you have alpha C square, alpha for C Q for voltage regulator, xi with capacitor bank, and gamma with the battery square. So, expected growth of this above Q's at different time step t can be measured by calculating the Lyapunov drift. That means, what is the Lyapunov function value now and what was at the previous time step. If the drift is minimized, if it is not moving, if the drift is 0, then you can say your Q length is also stable. If the Q length is stable, that means your operation of that quantity is not happening. That means you are restricting its operation. In order to keep the Q stable, we have to minimize the optimization goal and Lyapunov drift simultaneously. That means, not only you have to minimize the total cost, now you have an extra objective function to minimize the total Lyapunov drift simultaneously. So, minimization of this drift value will restrict the growth of the Q length and prevent it to move towards overflowing condition. However, restriction on Q length increment will cause more cost, right. That means, you are not allowing the battery to discharge, you are not allowing the battery to charge. So, what will happen? That will move to the more energy cost solution. Okay. So, hence a trade off between these two is highly needed with the help of weighted sum method. So, that we have done here. So, this is your Lyapunov drift and this is your actual cost function with a weighted value A. If you simplify this equation, above equation, and take the simplification, you will get that this is your total cost what you took before, and this is the function you are getting from the Lyapunov function. You can see here we considered a penalty for the load shedding, a penalty for the tap changing operation, a penalty with the Q for capacitor bank switching, and also for the battery operation, and they are all with their corresponding Q value. So, at the time started when t equals to 0, we know at that time C equals to also 0. So, when the time started, at that time your total penalty is 0. So, after that, at each time interval, whenever you will perform the load shedding or voltage regulator operation or capacitor bank operation, this Q length will increase, and that will enhance the penalty with the objective function, and that will restrict the operation of that particular equipment. So, the objective function has become linear, your constraints are also linear. Now, you can use only the linear programming for solving it, and also the time coupling with the future is also relaxed. You can see the objective function is only with the present time step, only with the t present time step. There is nothing with the t plus 1. Your battery coupled, your summation of that t for the voltage regulator, everything, all the constraints has been relaxed with this Q and the Lyapunov function values. Now we have to see whether actually your Lyapunov function is moving to the stable condition or not. So we are saying that Lyapunov optimization can obtain asymptotically stable condition and it goes to the optimal decision slowly, but whether it is happening or not, that we have to check whether our Lyapunov function is capable to do that or not. So the criteria for Lyapunov stability says a Lyapunov function shows asymptotic stability if it satisfied the following three conditions. First, at the origin the Lyapunov function value is 0. Then it should increase or it should be greater than 0 when at the neighborhood when it is not at the origin. And the increment of your Lyapunov function must be lesser than or equal to 0. That means it should decrease with the time. So this is our actual Lyapunov function. If we see, then we can see that at initial time step when t equals to 0, your Lyapunov function value is 0. Again, when the t greater than 0, at that time this is a square term, these are all square. So these are all positive term. So we can see that it is greater than 0. Now the dl, if you took the first order derivative, we can see that you will get dl by dc, dc by dt, then dl by dc, dc by dt, this kind of problem. So this is your dc by dt term, and as we are trying to minimize the drift, that means we are trying to minimize the enhancement of the q length. So always this will be lesser than equals to 0. So if they are lesser than equals to 0, then overall dl r by dt, that is also lesser than equals to 0. So that means we can say our Lyapunov stability is there. So our system is moving towards stable operation. So we are doing it for an MPOPF problem with a solution is iterative because we took the first order Taylor series expansion, and that expansion depends upon your initial solution. So if you do that, then your need of iteration, you need an iterative method for solve this MILP based problem. For initial value, you have to start the Taylor series evaluation, right. So you need an initial values. That initial value is taken by doing the integer relaxation. That means you relax all the integer values and solve the continuous with the nonlinear non-convex programming and get the near optimal solution. That solution is not optimal, but that is somehow close to the optimal solution. So get that solution, then start your iteration process. Okay, you, if it is not optimal, then go there, solve your linear programming. This is your MILP problem. Solve it and see whether stopping criteria is satisfied. That means your tolerance, it is lesser than the tolerance value. If it is not, then revise the Taylor series and again do the iteration, and if it is yes, then show the solution. Okay. So you may have three possibilities of the output, that either your solution is global optimum, or it is a suboptimal, or it is an infeasible. So if you are getting infeasible solution, then you have to reformulate your problem, then your something is wrong with your constraints. If it is a suboptimal, then you have to revise your initial point. Okay. So we have done this evaluation on the same IEEE 123 bus distribution network with this input data, and we have restricted the voltage regulator and capacitor bank operation for the total time steps 60 and 6, and we will see whether that is obeyed for the new method or not. So this is the offline greedy and proposed method simulation comparison. If you see that this is our price curve. So actually for offline, that means time coupled operation, offline means it is a time coupled operation. For time coupled, if you see that at higher time prices it is showing discharge, at lower time stage it is showing charge. Okay. So that we have to follow for our new real time OPF algorithm as well. It is mostly following, right. If you follow this yellow one, you can see it is mostly following. At the initial stage, this complementarity or this opposite behavior we have seen because there is some of a real time OPF. So it is following the greedy algorithm as well. But if you go only with the greedy, then you can think that at the peak price time with the greedy you do not have any power to discharge. That means it will goes to a costly solution. Again, if you see the time average load shedding, then you can see this is your quality of service limit. So, if you go with the greedy algorithm, it is not even allowing to do the load shedding. Okay? But if you go with the offline, then initial values it is very high load shedding, but it is slowly decreasing if you go with the proposed method. For offline also it is following the same trend. So, this new time decoupled method follows the offline and also has the benefit of the greedy. How? The solution time. See, the offline solution time is almost 40 minutes. That means you cannot have the time gap, or each time step is almost 40 minutes, but for greedy it is around 5 minutes, and that solution time we got even for our method. That is a new time decoupled method. But if you see the operation of the voltage regulators, for offline obviously that is less than 60, but for greedy, as we are not considering, so multiple times it is doing the tap changing operation. So, it has enhanced more than 60. So, that is not good, that is not obeying our long term benefit. But the new method, the time decoupled method, that is keeping that lesser than 60. The same thing we can see for the switching of the capacitor C2. Because of that, as it is not considering the long term benefit, you can see the cost of the greedy algorithm is highest, but for the time coupled obviously that is lowest. So, this time decoupled operation, considering the long term benefit, it is a trade off between your greedy and your time coupled solution. So, this is the overall computation complexity. If you see that you are solving for almost 3162 variables with almost 8500 constraints, linear constraints, and the initialization solution is taking 2-minute time. And per iteration of that iterative process, that is converging within 4 iteration, 4 to 5 iteration, is taking 55 seconds per iteration. So, the total average solution time is lesser than 5 minutes. So, whatever real time operation is still done in the power system, that is of 5 to 15 minutes time interval. So, our solution time is lesser than 5 minutes. So, we can see this time decoupled algorithm can be applied for real life application of the distribution network. So, with this I will end today's lecture and will continue with the new OPF technologies in the next class. Thank you.